Let's look at this example, just dealing with the graph of a cubic function and the properties of such a graph. We've got a graph which is representing y equals f of x, where a, b, and c are x-intercepts. So let's just note that. So point A, point B, and point C are the x-intercepts in the graph. Point D and E are the x-coordinates of the turning point. So point D and point E are the x-coordinates of your turning point. And H is the x-coordinate of your point of inflection, that point over there. Okay, let's just talk a little bit about this cubic graph for a second, and let's see, just a few things we can put together on it. First things first, do you notice this would be a negative cubic function? Okay, I know that because it's a d. So as x's are increasing on the x-axis, it starts off by decreasing, and the end behavior of your function is that it's decreasing. Okay, so what we could say is that as the x's are progressing along the x-axis, from negative infinity, all of these y values would be, or let me not say negatives, but they would be decreasing. They're getting lower and lower and lower up until that turning point, however, because from the turning point here to the turning point here, they're then increasing, but then obviously the whole function ends off by decreasing. So we've got a decreasing function. I'm just going to erase those red lines so that they don't cause any confusion. All right, what else do we know about it? We've got turning points, okay? Now, I'd like to point something out to you as a pretty important and quite a worthwhile thing to know. If you've got a cubic function, all right, and you've got two turning points, and let's say that you don't have the picture in front of you, so you don't necessarily know which of the turning points is your maximum point and which one is your minimum point. There's a very important and a very useful law that we can use called your second derivative rule, okay? And basically the second derivative rule does the following. If you want to determine whether a particular turning point is a minimum or a maximum, you work out the second derivative and you substitute the x-coordinate of the turning point into the second derivative. If your answer is greater than naught, so in other words, if your second derivative with that particular x value is a positive, then you know that that point is going to be a local minimum. So the positive value of your second derivative gives you the local minimum. And if you work out your second derivative and substitute an x value of a turning point in there, and you'll end up getting an answer that's less than 0. Can you see that you said second derivative is less than 0? In other words, it's negative. It means that you've got your local maximum. Okay, so please just learn that. It's a way of determining where is your local maximum and where is your local minimum by finding your second derivative and letting it equal to 0. No, not letting it equal to 0, working out whether it's positive or negative. If it's positive, it's a minimum. If it's negative, it's a maximum. Okay. Second derivative equals 0. That's your point of inflection. Okay, so that we just need to make sure we know as well. So point of inflection, which is this point here, is calculated by taking your second derivative and letting it equal 0. And your point of inflection, basically this part of your graph is what we call concave up. That's kind of your pointing up part of the graph. But there is a point at which the smiling shape of your cubic function turns into the frowning shape, and that's your concave down. And the point of inflection is the point at which it changed from being concave up to concave down. Okay, right, so what else can we talk about here? You've got your x-intercepts where y is equal to 0, and yeah, pretty much the rest of it we should be okay with. So this question is quite nice because it really tests our understanding of the shape of your graph. So it says write down in terms of the given constants the value for x for which. Okay, so the first one I'm interested to know is what values of x gives our f of x greater than naught. So for which values of x are my y values, because that's what f of x means, remember, for which values of x are my y values greater than 0? Well, let's just see over here. Do you agree that these y values, let's maybe try a different color, these y values are positive? Okay, so these are positive y values over here. as it dips below the x-axis, those are negative y values, but when it comes up above the x-axis again, those become positive y values again. So we can say that these are all positive y values and the rest are negative x or y values. So for which values of x is f of x greater than 0? It's going to be everything from negative infinity up to a, and everything from b up to c. So our solution there is going to be that x is an element. X is an element from negative infinity up to a. Now it didn't say less than or equal to. It just said, sorry, it didn't say greater than or equal to. It just said greater than. So therefore we're using round brackets. We use our union sign because we've got a gap between the values for x. And then it was from point B to point C. So from point B to point C is where those values, where the y values were greater than 0. For which values of x is the derivative equal to 0? So what do we interpret that as? Remember, derivative equals 0 means something very specific. What does it mean? It means the turning points. So for which values of x do we have turning points is essentially what that's asking. Well, where x is d and where x is e, and it's only those points. And if it's only those points, we represent them with curly brackets and we say point D and point E. The curly brackets are telling you that we're not taking everything between point D and point E. We're taking that point and that point. Done. Okay. For which values of x is my second derivative equal to 0? What was your second derivative equal to 0? That was your point of inflection. Okay, what is the value of x at your point of inflection? We said it was h. So x is an element of, and the x value at that point was h. Okay. For which values of x is your graph concave up? Concave up, the smiling graph. Let's change our color over here. Let's make it orange. So concave up is this part over here, but at that point it changed from being concave up to concave down, remember? So from negative infinity up to, in fact it's not at B, it's at H, your point of inflection. That's the point that it changed from being concave up to being concave down. So there we have, so where is it going to, what values of x? It will be from negative infinity up to your h. And again, I'm going to make it a round bracket because at point h it's neither facing up or down, so it's a point of inflection at that point. Right, okay, what do we have over here? For which values of x is your derivative equal to 0 and your second derivative is less than 0? So derivative equals 0, remember, is your turning point. And which turning point has my second derivative being a negative? Now remember we said earlier where second derivative is negative means it's your local maximum, and where the second derivative is greater than 0, it's your local minimum. So because this is less than 0, the turning point at which my second derivative would be less than 0 is my maximum, so that's at E. So x is an element of point E. That's where it would be a local maximum. Where is, okay, f of x is just y. So where is y less than 0 and my derivative greater than 0? So let's start with this. Where are my y values less than 0? Okay. My y values are less than 0. These are all my less than 0 y values. These are all my negative y values all the way along here. Those are all my negative y values, as well as over there. These are all my negative y values. Okay. Now, in addition to that, where is my derivative greater than 0? What does derivative stand for again? The gradient of the tangent. Okay, so if the gradient of the tangent is greater than 0, it means it's got to have a positive gradient. Okay, so if I were to, I'm just going to change the color of that line. if I were to draw a tangent to my function anywhere where I've got these red negatives, because it did specify where the y values are less than naught, I'm looking for where the gradient will be positive. Do you agree if I draw the gradient of my graph anywhere on this side, anywhere from here to here, okay, the gradient is a negative gradient. But from this point onwards, if I took my gradient and my line and I drew a tangent to the graph anywhere from this point onwards, so anywhere from anywhere from here to here, my gradient is going to be positive. And because the gradient is going to be positive, here's my positive gradient. Anything from D through to this x-intercept over here, which was B, I've erased it, but it was point B, is going to be where my y values are negative, but the gradient of my tangent is positive. All right. And if I were to draw the gradient of my tangent along these negative y values, well, again, it's going to be facing a negative gradient, so that's not going to work. So I simply need to write that between D and B is where my y values are negative and the gradient of your tangent is positive. So x would then be an element between point D and point B. Okay. And finally, where are your y values positive? Well, those are where the blue pluses are. The y values are positive, but the gradient of your tangent is greater than naught. So if I were to draw a tangent at any point along these blue pluses over there, the gradient would be negative. If I were to draw a tangent anywhere where these blue pluses are, this would give us a positive facing tangent. So anywhere from point B to point E, I'm going to have a positive gradient. And then as it turns over onto the other side, on this side, the gradient would be negative again. So it's only between point B and point E that I'm going to have positive y values and a positive gradient to the tangent. So between point B and point E. Point B, and let me just make sure I'm correct there, point B and point E, yes. Okay, all right, so there we go. So that's, yeah, quite a common type of question. You'll definitely get something like that along the lines somewhere in a calculus test. So again, it's about understanding notation. You need to understand that when we're talking about f prime x equals naught, we're talking about the turning point. You need to understand that if we're saying the derivative of x is greater than naught, we're talking about the gradient of the tangent is positive. The gradient of your tangent's pointing up, okay? If just f of x is greater than naught, well, just f of x means y. So then where are the y values greater than naught? So do you see that? If you understand each of those notations, then that makes that relatively easy to interpret. Okay, so go and watch that again if you need to, and just make sure you're listening carefully, stopping where you need to, just so that you can also process it and follow it to get to that final answer. All right, good job. We'll see you in the next video. Well done.